What else you got today? You know, no seminar,
Nope, no seminar today.
so just review session? Need to grade stuff or anything?
Maybe. Why? What's up?
I'm just asking. Like, after this review session, are you kind of done?
No.
Oh, what do you gotta do?
Well, I'm gonna go to the gym. I also have another review session at 1.
Okay, because I know you said June.
Yeah, gym and another review session at 1, which I'll probably just do at UNG. Okay, I'm gonna close the door just so it's a little quieter in here. But I love you. Hello?
Hey, what you doing?
I'm about to do a review session. Why?
Are you already at work?
No, I'm doing a review session at home. Why?
Oh, I was hoping somebody would bring me so fast.
I mean, I have a review session right now, so I can.
I heard that.
You can call someone else. I mean, Allie's still here. Mom, Melissa's here. Max is here.
Melissa's not there. Melissa's here. All right, play
Love you, bye. You gotta go. Stop. You go. You wanna do better.
Okay. Hello. Okay, here we go. Okay. So is everybody here? Everybody can hear me all right? Hopefully. Okay, so today we are just doing a review session for your upcoming test. You should have, I'm assuming you guys have an upcoming test. So if there are any questions that you guys have throughout, please let me know. If there's anything in particular you guys want me to go over, I can do that as well. Just like I said, let me know. So the first thing, can everybody hear me?
Yeah, I can hear you.
Okay, perfect. I'm like, I think you can hear me, but I'm not entirely sure. My computer doesn't always want to behave. So I appreciate it. Thank you. So the very first thing you guys learned, well, not the very first thing, but one of the very first things you guys learned from 1211 is the idea of dimensional analysis or unit conversions. And with dimensional analysis or unit conversions, this is something we use in order to go from one unit to another. So your given unit into a desired unit. So in order to go from a given unit to a desired unit, we're going to use some just regular algebra. And the idea that if you have something over something else that's the same, it will cancel out. And also the idea is if you have the same thing, if x is equal to y, then this term right here is equal to 1. And with algebra, we can always multiply or divide by 1. So that's kind of what we're doing with dimensional analysis. We're using these equalities where we have x being equivalent to y. So because they're equal to each other, we can essentially see them as 1. And as such, we can use them to go from one unit to another, a given unit to a desired unit. So we're just going to do a couple of examples that are on this conversion or on this review sheet. So first we're going from millimeters. Guess we have to sign in. Okay. Now can I write? How do I write? Draw. There we go. Okay. So we are going from 24.3 millimeters into nanometers. And I'm going to show you guys two ways of doing these metric conversions. So the first thing you need to do when you're thinking about metric conversions is think about how we go from our prefix metric unit into our base unit. So we want to go from millimeters into meters, and then from meters into nanometers. So I'm going to write both of these conversions. So 1 meter is equivalent to 1,000 millimeters, or we could also write it as 1 meter is equal to 1 times 10 to the 3 millimeters. We could also write it the other way, where we have 1 millimeter is equal to 1 times 10 to the negative 3 meters, but we're going to keep it like this. And then we can also go from meters into nanometers, where 1 meter is equivalent to 1 times 10 to the 9 nanometers. More than likely, your professor is going to require you to know all of your metric conversions for this first test. If you remember that just about all of them go by 3s. Why did that stop working? Sorry, one second, guys. What is going on? Sorry. What the heck? Why am I not? Sorry. Okay, there we go. Okay, so we can go from our 24.3 millimeters. We're going to go, whoa, stop, wow. We're going to use this one right here, where we're going to use meters into millimeters or millimeters into meters. We want to cancel out our millimeters, so that's going to be on bottom. So we'll have the meter on top, 1 meter, and then millimeters on the bottom. And again, because these are equivalent to each other, this is like multiplying by 1. And we can see that this will allow us to cancel out our millimeters and leave us with meters. Okay. And when we do that, we get 0.024 meters. Then we can go from meters into nanometers. So we want meters on the bottom this time. 1 meter is equivalent to 1 times 10 to the 9 nanometers, which will then be equivalent to 2.43 times 10 to the 7 nanometers. Okay, and that's probably, probably pretty common for you guys. I am going to show you one other method that I use that makes it a little bit quicker and easier. You may or may not get this. If it doesn't make sense, just stick with going back to the base unit. But another thing that you can do is you can look, and we see that 1 meter is equal to 1 times 10 to the 3 millimeters. Also, 1 meter is equal to 1 times 10 to the 9 nanometers. So these are equivalent to each other. Therefore, these are equivalent to each other. So we could say that 1 times 10 to the 3 millimeters is equal to 1 times 10 to the 9 nanometers. Okay. And another thing you could do is you essentially, to cancel out if you want to cancel this out, you will just subtract it from here. So we do 9 minus 3, which is 6. So we could also say that 1 millimeter is equal to 1 times 10 to the 6 nanometers. So if we know our conversion charts really well, we can get this conversion, and then we don't have to continuously go back into meters. So if we know what the meters are equivalent to, we can just use the difference between those in order to get to a easier to use conversion. And then what we have here is 24.3 millimeters. 1 millimeter is equal to 1 times 10 to the 6 nanometers, which would give us 2.43 times 10 to the 7 nanometers, which is what we got initially. Okay. All the rest of these are pretty easy. I will do one more. I'll do this one because it has megameters in it, and mega is one that a lot of people don't remember. And then we'll move on to significant digits. And again, if there are any questions throughout, please just stop me and let me know. Okay, so here we've got megameters. So we're going to want to go from megameters into meters, and then from meters into nanometers. So again, we're going to write down those conversions, and I'm going to keep them equivalent to each other. So I'll have meters on this side. So 1 meter is equal to 1 times 10. 1 second, I have to think about this. To the 6. Oh, no, sorry. Other way around. 1 times 10 to the 6 meters is equal to 1 megameter. And then we have 1 meter is equal to 1 times 10 to the 9 nanometers. Megameter is a larger unit than meters, so we're going to have more meters in it than we have in our megameters, but we can very easily put this into meters by essentially flipping and then changing the sign of the exponent. So 1 meter would be equivalent to 1 times 10 to the negative 6 megameters. Any questions about that? Again, I don't want to confuse anybody. That is not my goal. Okay. So now we can go, again, we could set these equal to each other if we would so like. So we could say that there is 1 times 10 to the 9 nanometers for every 1 times 10 to the negative 6 megameters. And we would do difference again if we would like. So we could do 9 minus negative 6, which be equivalent to 15. So we could have 1 times 10 to the 15 nanometers is equal to 1 megameter. Okay. And then it's really easy. We have 6.12 times 10 to the negative 7 megameters. 1 megameter is equal to 1 times 10 to the 15 nanometers. And that will be equivalent to 6.12 times 10 to the 8 nanometers. Okay, and again, you could do this the same way you did it before, where you go from your megameters into meters, and then from your meters to your nanometers. I just wanted to show you guys something you might not have seen that might make it a little bit easier to get through these problems. Okay, significant digits. Let's look at calculations in significant digits. So we're talking about significant figures. We either talk about it in terms of how many significant figures does a value have, or how many significant figures are we going to have after we do a calculation. So first, I'm going to look at how many significant digits a number has. When you are given a number, you're never really quite sure how many significant digits there are. But we have rules that are pretty good at telling us how many there are. When you take a value in lab, you should know how many significant digits there are, and you should write down every single significant digit. So generally, the values that you get in lab, those are going to have every value being significant. For instance, with a graduated cylinder, so if we have a graduated cylinder, and let's say it goes up to 10 milliliters, I'm going to zoom in just a second. We're going to zoom in on this part. And here we see that we have graduations every 1 milliliter, and then subgraduations every 0.1 milliliters. So when we have something like this, Okay. When we have something like this, that's not the right thing. We are going to report our value out to the 0.01 milliliters. So we can see that our number is between 9.6 and 9.7, and then we estimate that last digit. So I'm gonna say this is, I don't know, 9.62 milliliters. And when we do that, this value is our inexact value. It's our best guess. Right? And every single non-exact calculation, that last digit is going to be a guess at what the value is. Even on a scale, that last digit that's given by the scale is a guessed value. But it's a more accurate or more precise number than if I had just put it as 9.6. It is not 9.68 or 9.63 or something like that. It's our best guess is it's 9.62, which basically means it's at 9.62 plus or minus 0.01 milliliters. So that shows where we're uncertain at. That's the uncertainty in that value. So I actually technically put 9.63. But this is our best guess. So because we've made a guess on that last one, it still is a significant digit. So this value would have 3 sig figs. So every single value that you write down in lab generally will be a significant digit unless you're incorrectly reporting the values. But when we're given values, so if we're given a number, we need to use our sig fig rules to determine if a digit is significant or insignificant. So remember, anytime we have a non-zero, that is going to be significant. So it's kind of, we're thinking about the intention of putting down a number. If you're putting down a non-zero number, that was intentional. When you're putting down zeros, you have to determine, are these zeros significant or insignificant? That's one of the reasons why writing things in scientific notation is really the best thing you can do. But we have what are called leading zeros. So our different types of zeros. So leading zeros, these are zeros, zeros. Zeros before the first non-zero digit. So something like 0.00000002. These are all insignificant. We call these placeholder zeros. And anytime we have a placeholder zero, a zero that's just there to tell us the magnitude of the number, it is considered insignificant. And if we were to write this into scientific notation, 2 times 10 to the 2, 3, 4, 5, 6, 7, -7, we would see that those zeros would go away. So anytime you're writing in significant or in scientific notation, all of the zeros in there should be significant as a note. Okay, so leading zeros, they are non-significant. Trailing zeros, these are going to be zeros after the last non-zero digit. these are going to be significant when the number has a decimal. If it does not have a decimal, it would be insignificant. So if we have 100, this has 1 sig fig. If we have 100.0, this has 4 sig figs. And again, if we were to put these in scientific notation, they would look different. In scientific notation, this would be 1 times 10 to the 2. And then this would be 1.000 times 10 to the 2. So we would write them differently in scientific notation.
So basically, whenever you should basically check how many sig figs you have with using scientific notation.
You don't have to, because only if you know how many significant digits will you know what the scientific notation should look like. So I know what this looks like because I know that these are insignificant, so they would be dropped from scientific notation. But I have to still write those zeros if I'm writing it in the expanded form, because I can't just write 1. If I wrote 1, that's not the same number as 100.
Right.
So
Okay.
that's why scientific notation is so nice. So on the flip side, anytime you see scientific notation, anytime there is a 0, those zeros are significant. And it's because we've intentionally written those in, and because the numbers have a decimal. So you can see right here, this number has a decimal in it now, because it's in scientific notation, so we can see that those are significant.
Okay. Thank you.
Not a problem. Good question. Okay. And yeah, you guys can type in the chat or turn on your audio and ask questions at any point. So please ask away. Okay. Our next are captive zeros, or our last type are captive zeros. Captive zeros, sorry, I was never an English major. Okay, captive zeros are going to be zeros between non-zero digits. And these are always significant. These are not placeholder zeros, right? So these right here, these numbers are placeholder zeros. So they're zeros that are there just to tell us what the number is. When you have a non-zero digit, sorry, when you have a 0 digit between non-zero digits, that's actually what that value is. It's saying, okay, this is a 0 right here. So when we have 1000.1 or 100100, let's look at these two different numbers. Okay, these are captive zeros. These are captive zeros. So in both cases, those zeros are significant. So I'd say that this is a significant digit. This is a significant, significant digit, significant digit, significant digit, and then significant digit because it's a non-zero. And then we notice that there's this decimal place right here. So this also, this trailing 0 would be a significant digit. In this one, this is significant, this is significant, this is significant, and this is significant because we have our non-zero digits and our captive digits. And then these two trailing zeros are insignificant because they're just placeholders and there's no decimal in this number. Okay, any questions about significant figures in reported values? Okay, so let's continue on to significant figures or significant figure calculations. So we've got addition subtraction rules. and we have multiplication division rules. There's other rules beyond this, but I don't think we usually go over any other rules in 1211. So addition, subtraction rules. This is going to be by number of decimal places. That's generally how they say it. I find this is a little misleading personally, because it is essentially you're looking at whichever one has the digit of precision at whichever one has the digit of precision at a larger value, a larger place value, if you will. That's the one that you're going to round at. And what I mean by this is if you add together numbers 100 plus 20.0, the point of precision here is in the 100ths place. The point of precision here is at the 10th place. So when we add these together, we would get 120. We get 120, but we would round here, which would then give us 100. Does everybody see that? That's a little confusing, I know. Because a lot of people don't teach it this way, but our area of precision, our least precise value is the one that has precision out to the hundredths place. That's the greatest precision it has. Well, this is out to the tens place. So we'd have to round at the hundredths place. Mostly you're going to see values where you have decimals. So you have like, I don't know, 0.025 plus 0.10010 or something like, I don't know. And when you add these two together, you get 0.1251 and then we would look, this has precision out to the thousandths place. This has precision out to the whatever that is. I really don't know. So this would be the less precise value. So we would round here and our value would end up being 0.125. Okay, so addition subtraction rules are oddly enough harder than multiplication division rules. When you guys get in, and you might already be here, but when you start doing atomic calculations, that's where these addition subtraction rules come in and get very dicey. So when you're doing multiple steps, you have to think about where the last digit of precision is according to the sig fig rules all along before you get to the end. And then at the end, you have to actually look. I think there might be an example of that where I can show you in the work, but I just want to go over that first. Okay, multiplication division rules. Least precise value. So in this case, fewest number of significant digits. This will determine the number of significant digits of the answer. So this no longer has anything to do with decimal places. So if we have the number 255 times by 1000.011, we see that this value has 3 significant digits. This value has 7 significant digits. Our answer will therefore have 3 significant digits. So let's multiply this out. 255 times by 122. This gives us a value of 25502.805. And we're going to start from our left, go over 3 digits. 1, 2, 3. And then we are going to round at this spot. So we see that this is 0. So this is going to stay a 5, giving us 25500. Do not write 255. Don't just get rid of the rest of it. You still need to keep these place values in there. And if we want to write it without any ambiguity, we could write it as 2.55 times 10 to the 4. So writing it in scientific notation removes any ambiguity that might exist. Okay, any questions about any of that? Okay, so again, if there are any questions, please just stop me. Here are a couple of examples of rules and stuff like that. So we are going to always remember, please excuse my Aunt Sally, my poor Aunt Sally. Please excuse my Aunt Sally. So you have parentheses, exponent, my dear Aunt Sally. Sorry. It's please excuse my dear Aunt Sally. So you do parentheses, exponents, multiplication, division, addition, subtraction. All right, so you follow it in those rules. Of course, multiplication, division is together, and addition, addition, subtraction is together. So when we're looking at something like F, we're going to do our multiplication first and then add in. So let's try that one out. So F, we've got multiplication division rules first. That's by significant digits. So when we multiply these two numbers together, at the end, our answer should have 3 significant digits. And then when we add this number and this number together, well, first let's start with the first part. So when we multiply 147.1 by 12.5, we get a value of 1838.75. Okay, and we're going to round to 3 significant digits. So we would round here. Now, I don't round to the end, but I'm going to go ahead and write a little mark over there so that I know where I'm going to be rounding later. And then I add my 13.1. And that gives me 1851.85. But again, our point of precision is in the tens place. So I'm going to round at the tens place here as well, giving me 1850. Or again, with no ambiguity, 1.85 times 10 to the 3. Okay.
So
Okay.
could you explain how you got the so I know we're doing like the most precise number when you're multiplying.
Well, it's the number of significant digits. So we see that this has 4 sig figs, this has 3. So our answer has to have 3 sig figs. So we start from our left, 1, 2, and then 3, right?
Yeah.
So we're going to round at this point, but I don't round until the very end. Especially since online homework programs, Chem 101 or Mastering Chemistry or whatever you're using, they usually won't round their digits or their numbers until the end, but they're still going to expect you to know where you should be rounding.
Okay.
So I see according to multiplication division rules, I would round at the tens place. So then this is the same as saying 1840 plus 13.1. And we can see a little bit more clearly that. And then when we put these together, 1853.1, we'd round here, giving us 1850, which is the same number that you get here.
Gotcha. Thank you.
No problem. Okay, so let's try. Is this just dimensional analysis? Okay, there is naming on here. I was like, oh goodness. Okay, let's look at a little. We're just gonna try one of these dimensional analysis problems. I'm gonna try and find one that's a little harder. Density of mercury. Okay, let's try this one. Okay, so we've got 25 times by 25 times by 10. So it's talking about a swimming pool. Swimming pool, we can assume that this is going to be a rectangular prism. So it's gonna be something like this. And we can figure out the volume of this tank by taking the length. By taking the length times by the width times by the height. So 25 times by 25 times by 10. And when we do that, we get 6250 meters cubed. You're multiplying the numbers and the units, and anytime you multiply units together, you just add their exponents. So if we write meters, that is meters to the 1. So it's meters to the 1 times by meters to the 1 times by meters to the 1. So it's meters to the 1 plus 1 plus 1, which is meters cubed. So if you're multiplying exponents, numbers with exponents, you add them. If you're dividing, you subtract them. Okay. So now we need to think about how meters cubed is going to be related to milliliters. And we should know, hopefully, that one centimeter cubed is equal to 1 milliliter. So we can go through, we can convert this from meters into centimeters cubed, and then we have a direct conversion from centimeters to milliliters. So remember, 1 meter is equal to 100 centimeters. And you can set this up 2 different ways. You could go 1 meter, 100 centimeters, and then take the whole thing and cube it. But I think it's a little bit easier for newer students to dimensional analysis to just do this 3 times. Keeping in mind, every time you divide, you're subtracting. So this would be 3 minus 1, which gives us 2, 2 minus 1, which gives us 1, 1 minus 1, which gives us 0. So that will completely cancel out your meters. And then centimeter plus centimeter, or centimeter times centimeter, we give centimeters cubed, because that's 1 plus 1 plus 1. So that's going to give us 250. So if we just multiply by 100 3 times, we get a very large value of 6.25 times 10 to the 9 centimeters. We can then take that value right there And, I'm sorry, centimeters cubed. We can convert that into milliliters. So 6.25 times 10 to the 9 centimeters cubed. 1 centimeter cubed is equal to 1 milliliter, giving us the same value in milliliters. And then we can take this value and multiply it by 13.6 grams. To give us our gram value, which would be 8.5 times 10 to the 10 grams. And now that we have that, we need to go from grams into pounds. So we need our gram to pound conversion, which I can never remember. There we go. Where 1 pound. 1 pound is equal to 453.6 grams. Giving us 1.874 times 10 to the 8 pounds. And then we look back. This is all multiplication here. So technically we should be at 1 significant figure for this. So 2 times 10 to the 8 pounds would be the correct answer here. Keep in mind, a lot of times your unit conversion factors are inexact. This one is inexact. The only exact ones you guys probably know by right now are metric conversions are always exact. And then 1 inch being equal to 2.54 centimeters is exact. If you have exact values, you consider those value or exact conversion factors. You don't consider those conversion factors when you're thinking about significant digits. Generally, you can use a given number at the beginning to figure that out, but keep in mind, sometimes you do have to look at your conversion factors. And almost always your dimensional analysis is going to be multiplication and division. Very few examples where there's not. So you're just going to look through and find which number is the least precise that you multiplied or divided by. Here, that value is 10 because 10, since there's no decimal there, has 1 significant figure. So our answer will have 1 significant figure. Any questions about that? Okay, there is one other way I want to show you guys how to do this one. Because what I did specifically because I wanted to show you guys the conversion when you're doing a cube. But we could have done this a little bit easier. We could have, if we remembered, okay, 1 centimeter cubed is equal to 1 milliliter. We could have then thought, okay, if I get these into centimeters, then when I cube it, when I multiply them all together, I won't have to do anything else. So remember, 1 meter is equal to 1 times 10 to the 2 centimeters, or 100 centimeters. So 25 meters. This would give us 2,500 meters. Right? So this would be 2,500 meters, sorry, centimeters. Times by 2,500 centimeters times by 1,000 centimeters. And now when we multiply them all together, we'll already be in centimeters cubed. the 6.25 times 10 to the 9 centimeters cubed. And then that's the same as 6.25 times 10 to the 9 milliliters. And then from there, we can do the rest of the multiplication and division that we did a minute ago. But just wanted to point out, if we had already put them in centimeters, that will make our lives a little bit easier. Okay, and I'm also going to do number 6 because it has units on the bottom. So we've got a slug that is moving at a speed of 0.075 meters per minute. And it wants to know how many years it'll take the slug to travel from Los Angeles to New York, which is 2,800 miles, where 1 mile is equal to 1.61 kilometers. So we need to go from meters into miles, or we could do it the other way around. Either one's fine. And we need, so we're going to need to be going between those two, and then between minutes and years. So we need to think about all the conversions that we need to go from one to the next. So we already have miles and kilometers, so we know we need meters and kilometers, and then we have our kilometers and miles. And then minutes to years. I guess it depends on how many you remember. I don't remember any of them, so I'm going to go from minutes to hours to days to years. Right? Because I don't remember any of it. Okay. Now, at the end, we want years, right? So we need to have our time unit on top. So that means that this conversion, when we do it, we need to have minutes on top, which means we want to have that meters on the bottom. And if we think about how dimensional analysis works, the desired unit you're going to have, to cancel out its old unit, it has to be on the bottom. So I am going to go and start out with my 2,800 miles. Because when I multiply this out, if I finally get this into miles per year, I actually want this to be flipped, right? So that I get the years on the top, if that is making any sense at all. Okay, so I'm gonna convert this from miles. I'm gonna go ahead and get this into meters. So I have 1 mile is equal to 1.61 kilometers. And then 1 kilometer is equal to 1,000 meters. Okay. 2,800 times by 1.61 times by 1,000 gives me 4.508 times 10 to the 6 meters. Now I can go ahead and use this. So I have 1 minute, 0.075 meters. Okay, and we divide that out. I get a very large value, 6.01 times 10 to the 7 minutes. Now I can go from minutes into years. So there are 60 minutes in an hour, and then there are 24 hours in a day, and then there are 365 days in a year. I'll take this value, divide it by 60, divided by 24, and then divided by 365, giving me 1.14 times 10 to the 2 years, or 114 years. But we do need to be at 2 significant figures, so I would go at 110 years. Wow. Take them a long time. Okay. Any questions about any of that?
Yeah, how did you know that you needed to have like minutes on the bottom or years on the bottom and stuff like that?
So I knew, because it's asking me how many years, that my answer was going to be years. So my answer was the time component of that. So since we're using a speed, a distance per time, I actually, since I want time on the top, I'm going to have to flip it.
Gotcha.
And since I knew I was flipping this, I then thought about how I would deal with this. Since this is going to be flipped, and it had the distance measurement on top, when it's flipped, the distance measurement will be on bottom. So I'm going to start out with my miles, so that I'll have miles going to meters, and then I'll cancel it out with those meters on bottom. So it's just starting to think about, I always start with what my answer is supposed to be. And then I think about what unit conversions I have. I know I have years. I know I have years, and that's my answer. So at the end, I'm going to have years. Right? At some point I have, and I'm just going to put this as time. And then I have a distance over time. And then I have a distance. So those are the things that I'm given here, right? Distance over time, time, distance. So since I want to be at time, I need time over distance here. And then in order to get rid of that distance, so that'll cancel out my distance and leave me with time.
Okay, that makes more sense. Thank you.
Not a problem. I was like, not sure what else to say. So yeah, you can think about it theoretically before you even put values in. Okay, on to naming. Has everybody gotten into naming in their classes already?
We haven't had lectures on it because our teacher's been sick, but she put up the chapters. I think they are up.
So are you guys learning naming on your own then?
For my class, yeah, I think we are, because we haven't had any lectures.
Okay, well, that's good to know. I will do a more lengthy naming component then. So if you guys are, I just want to make sure you guys hadn't not gotten into it and not supposed to have gotten into it yet, because then it would be really just confusing probably. Okay, so naming. When we talk about naming, we do naming by the type of substance it is. And we call the IUPAC method of naming. So the IUPAC method, not really important to know what that means, like international, I don't remember what it is. It's international something, maybe chemistry at the end. I'm not great with memory. But it essentially it's a systematic way of naming everything so that you have a unique name. And if you know what type of substance it is, you can take that unique name and come up with the formula without there being any ambiguity. So we are going to look at the naming of binary covalent species. So AX, BY, where A and B are nonmetals or metalloids. So anything but a metal. And then we're going to also look at ionic compounds. And these, they're still going to be binary, but so it's going to be AX, BY, where A is going to be a metal or a positive polyatomic. I guess it should be metal cation. So either way, A is going to be a cation. So it'll either be a metal cation or a positive polyatomic. And within the metal can be, the other way. The metal can be main group. So alkali metals, alkaline earth metals, or over in group 13, like aluminum or gallium, or they can be non-main group. And they're going to be named differently. The non-main group, that's going to include all of our transition metals, our lanthanides, and our actinides. So if we think about the periodic table and the way it looks, these are generally considered main group. These are considered non-main group. Okay, so that's our A, and then our B is a non-metal anion or a negatively charged polyatomic. So we're gonna have a cation plus an anion, essentially, in this type of naming. And this is gonna be the most common name that you guys are going to see. And then we're also going to have acids. We're going to have HX, BY, where H is hydrogen ions, and B is an anion of some type. So it could be either of these types of anions. Okay. You should also, if you have not already started to memorize your polyatomic chart, do that. Start as soon as possible, because any chemistry class you take from this point forward, it's going to be kind of expected that you guys memorize or have the polyatomic ions memorized in your head, which is where it'd be memorized, but sorry. So make sure you know the polyatomics. Okay, so I am going to start with the binary covalent because they are the easiest. So binary covalent, something like, I don't know, N2O5. So this, your A, so that's our A, that's our B. Your A, you're going to have a prefix that indicates amount. So the X value. And then it's going to be the element name. So this would be dinitrogen. And then for your B, you're going to have a prefix, which indicates the amount of Y. and then your element name, but with a IDE ending. So you're going to drop its regular ending and put IDE. So instead of oxygen, this would be oxide. So this would be dinitrogen tetroxide. Okay. So there is a whole list, and I don't have the list in my iPad, but there's a whole list of those prefixes. They should be found in your book. Di, tri. I don't even remember because I never name binary covalent compounds. Oh, sorry, this is supposed to be penta. No wonder. Sorry, guys. Pentoxide. So mono, di, tri, tetra, penta, hexa, hepta, octa. Was it nano after that? Nana, deca. So 1 mono, 2 di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, 10 deca. I don't think you'll need to know any more than that, but now there are some notes about this. If you're a element, there's only one. You do not use mono. So if you have NO2, this would be nitrogen dioxide. Okay. If you have other note, if you have A and O together, so this was, we have penta adding to oxide, you're going to drop that A to give pentoxide. So you're going to drop the ending of your prefix. So drop vowel of prefix. If your prefix ends in A and your the beginning of your elements begins in O. So this, again, not very common, but usually pretty easy for people to do, as long as you can remember these, which I don't always. Ionic naming, much easier for me because I remember all of it, but it'll be a little more difficult for you guys at the beginning. So ionic naming, this one, we don't use the same designations, mono, di, tri, tetra, blah, blah, blah. We are instead going to take advantage of the fact that we're dealing with ions, and as such, they need to balance out to a neutral charge if we have a compound. So if we have something like NaCl, sodium is a metal, it'd become a metal ion. Chlorine is a nonmetal, it'd become a nonmetal anion. So we know that this is made of Na plus and Cl minus. Now, do you guys know how to use the periodic table to predict charges? Do you guys need me to go over that? Guessing I don't? If you guys do, just let me know. So let's first look at when we're naming these ionic compounds, we're going to name them. The naming scheme we use is going to be based on what kind of cation we have. So if we have a main group cation, these are all ones that we can use the periodic table to predict the charge. So as such, we don't need to indicate charge here. We're going to be able to use the periodic table to determine that. So we know our alkali metals, when they're cations, they're always going to be +1. Our alkaline earth metals, they're always going to be +2. And then our aluminum and gallium, I guess. What do they call that group? So, I mean, in general, it's just going to be, I guess we could go with group 13. The one that starts with boron. And boron, I guess we can include in there, although it's less common. It's usually technically more non-metal than metalloid or metal. But regardless, these will form +3 cations. So we know if it's an alkali metal, an alkaline earth metal, or a metal within group 13, we know it's going to form a +3 cation. So we don't need to designate charge for those. So when we name these, we're going to name the element. So I guess I should do. We have A, X, B, Y. A is going to be named as the element name. And then B is going to be named as either the polyatomic name for main group, right? Or we're going to use the element name with a IDE ending. So NaCl, sodium would be just sodium. And then Cl would be it's chlorine. So we're going to drop that ending and it becomes chloride. I personally suggest remembering one of each type. That's easy for you to remember because then you can extrapolate the naming rules from that. Sodium chloride, most people know that name. So if we look at that and we have sodium chloride in our head, we can then figure out how to name any other main group element ionic compound. Okay, next we have our non-main group cation ionic compound. The problem with non-group is we have a cation that can have a variable charge. So iron can be +2, +3. Copper can be +1, +2. Manganese, I think, could be +4, +3, +2, +1. So we have plenty of different charges. So we need to use our name to indicate which charge it is. So we're going to have our A is going to be the element name and then a Roman numeral. That indicates the charge, not X. Not X. It is not X. So, and then B is same. We're not going to change the way that we name B. So let's take Fe2O3. Now, when we see something like this, the first thing we should note is that we have no idea what the charge of iron is. But we always know our anion charge. So oxygen is in group 16. That's 2 away from 18. So that means that oxygen is a -2. And if you're never really sure, you could take, for your anions, you could take the noble gas. Sorry. Let's do that the other way. You could take its group number minus 18 to determine what its charge is. So for oxygen, its group number is 16 minus 18 gives us -2. The nitrogen group is 15, so it'd be -3. The halogen group is 17, so it'd be -1. Okay, so we have oxygen at -2. So that means that this portion of this compound is -6 because there are 3 oxygens. That means that this portion of the compound must be +6 because there are 2 irons. We take +6 divided by 2. That gives us +3. So each of our irons are +3. We can then name this as iron 1, 2, 3 oxide. So this is iron 3 oxide. Does this make sense? Okay, let's keep going then. Those are really the only 2 ways to name things. You're going to, do you have a main group cation? Then you just name it as its element name. We usually do transition metals, but non-main group, you need to indicate the charge. There are a few exceptions. Specifically, zinc will always be zinc 2+ in an ionic compound. So we do not need to use a Roman numeral for zinc. Silver will always be silver+. So we do not need to use a Roman numeral. So if we have ZnO, this is just zinc oxide. If we have Ag2S, this is just silver sulfide. Okay. But other than these 2, all other transition metals, you're going to use a Roman numeral. You'll also use a Roman numeral for the metals that are underneath the stair step. So stuff like lead and tin and indium. So these are metals. And they also have variable charges. Lead can be 2 or 4. I think tin can also be 2 or 4, and then indium is usually 3, but it can also be 4 as well. Okay, any questions so far? Okay, the last thing is naming acids. Acids are going to be named based on the anion. So the anion determines the anion is the only thing that's really changing because we're taking an anion and we're just adding hydrogen ions until we balance out the charge. So if we have something like Cl-, if that is our anion, to make an acid, since it's actually gonna write Cl1-, our charge is 1-, so the magnitude is 1, so we're going to have 1 hydrogen. So our acid here would be HCl. So this is our anion, and then our acid. Our anion, this is a simple anion. So it would be chloride. When we're making a IDE ending anion into an acid, we add the prefix hydro, then we'll have ic acid. So it would be hydrochloric acid. So there's that chlor in there. And this is the one that I usually tell people to memorize to have a basis for names, because most people know hydrochloric acid. That's something you can come up with without much thought. And then once you have that, you know that you have the hydro prefix and then the ic acid suffix. Okay, if you have a polyatomic anion, you have two different types. You have one with a ATE ending, and then one with a ITE ending, and they're going to be named differently. ATE ending, it's going to go from ATE ending to an ic acid ending. So SO4 2- is a good example of this. SO4 2-, this is sulfate. We have 2 here, so we're going to need 2 hydrogens. So this would be H2SO4 in our acid form. This would be sulfuric acid. This one is a little weird because it's sulfur. I think they named this one because it sounds better. So let's actually do another one. PO4 3-. This is phosphate. And then we have a 3-. This would be H3PO4, which would be phosphoric. I guess it all does that, doesn't it? Oh, it does that too. It's almost like it goes to ric acid instead of, but not quite. But regardless. Okay. Again, I usually suggest people remember sulfate, sulfuric acid. We also have another one, NO3- nitrate. This is a 1, right? So it would be HNO3 nitric acid. This one works, right? There we go. Nitr, and then ic acid. So the AT ending drops and we get ic acid. So if you try and go phosphoic acid, that sounds weird. And then sulfic acid also sounds weird. So I think they just add that and or in there to make it sound less weird. Okay, ITE ending. So this is the polyatomic that has 1 fewer oxygen. So this would be SO3 2-, PO3 3-, and NO2-. So it has the same charge, but it has 1 fewer oxygen. So this is a little more room. This is going to be sulfite, phosphite, and nitrite. So they all have an ITE ending. You're going to convert the ITE ending into us acid. So this becomes sulfurous acid. Phosphorus acid. And nitrous acid. As a note, if you have a prefix, so remember ClO4 minus, this is per chlorate. So keep that per in there, and it becomes per chloric acid. Or if you have ClO minus, hypochlorite becomes hypochlorous acid. Any questions? It's a lot, especially if you are learning this on your own. But let's try a couple of examples and then we'll call it quits for today. Okay, so let's start with this one. Actually, let's do C and D. So C is PbNO3 2. So PB, well, PB is underneath the stair step, so we know it can have a variable charge. So I always like to start out with my anion if I see that my cation is not main group, like this is a main group, this is a main group, this is a main group, this is a main group. So those we already know the charge of, but this one we're not sure. So we look NO3, that's nitrate that has a -1 charge. So this will be -2. So our lead is +2. So this would be lead 2 nitrate. Okay. Let's try this one now. We have Cu2CO3. So copper is a transition metal. We need to start out with our carbonate. So carbonate is -2. So this whole thing must be +2, but there are 2 of them. So we do +2 divided by 2 gives us +1. So this is copper 1. So we do copper 1 carbonate. Real quick, I want to point one more thing out. You can have polyatomics where you add hydrogen ions, but you don't get to a compound. And we name that a special way. So if you have CO3 2- and you add 1 hydrogen, that gives us HCO3-. This is carbonate. This is hydrogen carbonate. It's also called bicarbonate, but that's a common name. PO4 3-. Let's add 2 hydrogens to that. Be H2PO4-. This would be dihydrogen phosphate. So it only becomes an acid if you completely neutralize the charge. So you have to have as many hydrogens as the magnitude of the negative charge. Otherwise, you'll add hydrogen or dihydrogen to the name. Sorry, I meant to point that out, but I forgot. Okay, these 2 right here, these are completely non-metal, so they'll be binary. So SF2 would be, there's 1. Where did it go? Why is it? There's 1 sulfur, but it's at the beginning, so this would just be sulfur. And then there are 2 fluorines, so it'd be difluoride. The next one 1 phosphorus, we just call it phosphorus. And then 5 fluoride, so pentafluoride. We have something like NO. This would be nitrogen monoxide. We do need to add that mono. Oh, and also if you have 2 O's together, you'll drop the O. Okay, let's see. Let's do these two just to remind us what these are. So both of these are main groups. So we don't need to use any sort of Roman numeral for these. So it's just calcium. And then that's CN, that's cyanide. So this would be calcium cyanide. And then aluminum, I don't know why I give it a capital, does not need to be capital. Aluminum phosphate. Okay, and then going from name to formula, we just kind of look. So iron 3 chloride. With this, I always suggest you write out the charges. So we have iron 3 plus, and then chloride. Chlorine is in group 17, so it'd be 1 minus. And here you're going to take the charge, the magnitude of the charge, and it's become the subscript of the other one. So this is going to go over there. That's going to go over there. So we're going to have iron 3 chloride. It'd be 1 iron, but we don't need to write that in. And then 3 chlorines. Oops, but we do need to have that E in there. Okay. Lithium chlorate. So chlorate, that's part of that 4 series where you have ClO 4 minus, ClO 3 minus, ClO 2 minus, and the ClO minus. This is perchlorate, then chlorate, then chlorite, then hypochlorite. So chlorate is this one right here. So it'd be Li plus ClO3 minus. They are equivalent charges, so they'll be 1 to 1, where we have LiClO3. This one right here cannot be named or cannot give us a formula because chromium is a transition metal. So this is incorrect. Let's do this as chromium 3 nitrate. Do chromium 3 nitrate. So chromium 3 nitrate. So again, cross, we'll have 1 chromium and then 3 nitrates. As a note, if you have a polyatomic and you're going to have more than 1 polyatomic, you need to put it into parentheses. Okay, I think with this, you guys should be able to do the rest of it without any issues. Make sure to review your polyatomics. Oh, I didn't actually. I don't know why. Apparently my iPad's also done because it just stopped. I don't know what's going on. Anyways, but I will go over any more things you guys want me to go over if anybody has any questions or wants me to do any other examples of anything. So, what do you guys want? If the answer is nothing, you guys are free to go. I did record this, I think. I meant to. Yep, I recorded it. So I will make sure this goes up on D2L. I will also put the key up for this worksheet momentarily. Okay, have a great day, guys. Great weekend.